Switching to you, Matt. Can you quickly switch to your webcam, please?
Great. Yes. Can you hear me?
I can't hear you. I don't see you though.
Um,
It's probably on Zoom.
I am showing the, let's see here. I'm showing that my video is live.
There you go. You're live.
All
Got
right.
you. All right. It's all yours, Matt. Take it away.
Or,
Thank you.
Thank you. So, good morning, good afternoon, good evening. My name is Matt Bacanti. I'm joined here today with Jesse Hoskins, and as Ramon had mentioned, we're going to be talking about an open source workflow for advanced vehicle dynamic simulation. So the first thing I wanted to touch on is that this is a very broad subject area, a tremendous amount of information that can be discussed in the overall dynamic and the different tool chain that can be used to address this. In fact, the OpenVSP, which Jesse will be talking about a little bit later, has an entire conference track and information associated with it. So our objective today is to work through a high-level overview of this information to arm you with information of how you could best use this in your development workflow and process. And while we mentioned an entire different components of the workflow, you see those identified here up on the slide, the two specific areas we found most valuable and interesting are OpenVSP and JSBSim. And given the amount of time that we have today, that's what we're going to be focusing on. So what we're going to be covering today is the why. Why would you use this particular configuration? At a high level, how? And then some demos, the what you can support and do. Again, we want to make sure that people come away from this presentation with an understanding of this at a high level, and to be able to identify critical flight control characteristics of their vehicles and simulations. Another note is that the information we're sharing here today is not the be-all, end-all solution. There's multiple different ways that we'll talk about that you can support, but this we found to be meeting kind of that golden 80-20 rule, where we're identifying those 20% of inputs that are driving 80% of the outputs, and specifically how that relates to the broader performance of the vehicle itself. Now, jumping into a high-level implementation here, and that is how the back-end SITL solution is actually functioning. So first and foremost, the work that has been conducted here has been heavily supported and influenced by a number of different individuals, including team members that we have in Mexico, Poland, and in the US, as well as adopting a lot of the great work that the open source community has published. Specifically, we'd like to recognize Roman and the work that they did originally on some of the Hill work, which we've taken and adopted and used for this particular scenario. If you look down on the bottom, when we look at the two key components that we wanted to focus on, one is this airframe definition with OpenVSP, and two being JSBSim. The interaction between these two is the specific area of workflow we'll be focusing on. But another key input that we wanted to identify was the fact that this implementation is slightly different than using FlightGear in a standalone fashion. And we'll talk about specifics of how that affects it. But ultimately, the key is that we can run JSBSim at a much higher rate than you can run FlightGear at. If you're familiar with any of the general PX4 software in the loop or hardware in the loop concepts, this is leveraging all of those same configurations and components. So why? Why did we go down this path? We started this process about 9 months ago when we were integrating a new airframe with PX4 and new avionics and payload packages. Inherently, that was adjusted the mass distribution of the airframe. We wanted to ensure the changes that we made on this large airframe weren't going to have adverse effects on the overarching performance. And obviously, if you're going to be flying a 45-pound airframe, this is not inexpensive, and it carries a significant risk from an overarching operational perspective. So we want to identify any of those really exciting components of the airframe characteristics prior to actually going and flying the vehicle. And so in that process, the first step that we took was to conduct basically the paper napkin exercise of doing an assessment of the vehicle. And we determined that this particular vehicle, with the initial configuration that we had identified, had a static margin that was smaller than we would have expected. And for those of you who may not be familiar with static margin, ultimately it is the it ultimately derives the fact of how the vehicle performs when it is up against some of the flight envelope characteristics, which would be interesting and important to identify when we're doing a back transition, since this is a VTOL or a forward transition. And so we took the opportunity to model the airframe, effectively creating a digital twin that allows us to go take that vehicle, evaluate it, train it, give our flight crew members the opportunity to actually see and feel the vehicle in the simulated environment, plus identify the way that we could either improve that static margin or overarching increase the performance of the vehicle prior to actually conducting that first flight. So now I'm going to hand it off to Jesse, who is going to take us through the next steps, specifically related to the why and how and the what. And I look forward to chatting with you more at the end here in the Q&A. Jesse.
All right, thank you, Matt. So today I'm going to start out by talking about the why with selecting the tools that we did. So we broke the tool chain down into two primary tools. First, an aerodynamic analysis tool. So the table at the top left here, you see that OpenVSP and VSP Aero. That's what we ended up picking. But basically, it's an open source NASA tool that has a linear vortex lattice method solver. Also has a panel method solver to perform aerodynamic analysis. So this level of analysis we found to be sufficient. It's also an open source tool, has a very easy to use GUI. Again, like we had said before, it has a workshop specifically dedicated to it, so it's pretty well supported. We also looked at DigDat, which is the program now that is the digitization of the Air Force's DATCOM framework. So it's a very sophisticated framework, has a lot of history behind it. It's mostly open. There's some GUI components and plotting components that are closed, but one of the things that we noticed was we were looking to model an A-tail, and so some of the complex geometries drove us closer to OpenVSP in this case. We also looked at AVL, which is more of an industry standard tool for this type of analysis, which is sophisticated, it is open. However, we found the learning curve to be non-trivial. So in this case, kind of similar with MATLAB and Simulink in that with the aerospace toolbox, it's very powerful. It's often used in concert with a DATCOM type tool, but it isn't open. It's also probably a little more of a learning curve than we were looking for here. So next we went to flight dynamics simulators. So looking for a 6 degree of freedom simulator that was of sufficient complexity. So JSBSim is what we ended up settling on. One of the key things about JSBSim is we were able to run it at 250 hertz and beyond on relatively limited hardware resources. It's also very open and extensible. It can be complex to configure initially at times, but it's very extensible. That was key for us here. We also evaluated X-plane, the hardware resources required to run at 250 hertz, which is obviously what we'd like to be the EKF and PX4 at, were a little more substantial. And so that combined with it not being open lent us towards JSBSim. We ended up using FlightGear here for the visual front end, but not the dynamics Basically, it's more constrained than JSBSim. And we also looked at RealFlight, which is a very good tool. We could run that up at 250 hertz, but it's not open, and that was something that we really wanted to have here. Obviously, Gazebo was another tool, basically the first simulator that we evaluated, and it could function in this capacity. There were some elements of JSBSim and how the dynamics were implemented already that moved us that way, but Gazebo would also be a completely fit into this framework. So now I'm going to switch to the how. So specifically with OpenVSP, we wanted to take a model of the vehicle, so the geometric and mass properties, and create or perform an analysis to generate the aerodynamic coefficients, stability derivatives, things like that. So on the right side of this slide, we have the mass properties specifically is where we'd start. So there's a lot of ways to model mass properties in OpenVSP. We chose to use point masses, and using the inertial calc tool in OpenVSP, able to generate the center of gravity and moments of inertia around the 3 axes. We then took the geometric properties and built a geometric model in OpenVSP. Now, one of the key insights in OpenVSP is how the solvers are set up, specifically within VSP Aero, which is kind of the, I'd say more the back end of the aerodynamic analysis. The simpler geometrically, the better it will perform. Specifically with the vortex lattice method that we were using, since everything is modeled as a lifting body, mainly the dominant aerodynamic components should be modeled. So that's your wings, your control surfaces, your stabilizers. Everything else contributes to drag. We did have another method of building up drag that OpenVSP, the workshop actually recommends. So we found it to be sufficient to model the wings, control surfaces, and stabilizers. So with that geometric model, we were able to iteratively run VSP Aero. So you can do computational sweeps over varying flow conditions. So your angle of attack, your side slip angle, Mach number, control surface deflections, etc. So we were able to pull out the aerodynamic coefficients, ground reaction forces, stability derivatives, even model rotor wash effects as well. So moving to JSBSim, now we wanted to leverage the JSBSim airframe definition model and framework, as well as what we had from OpenVSP to generate our digital twin. So on the right, we kind of broke out the major sources of information that go into the JSBSim model. Again, JSBSim is pretty well supported. There's a lot of documentation online about how to do this, but it's kind of the breakdown that we came up with. So starting with kind of your metrics, so those are your areas, visual reference points, sorted reference points in the JSBSim XML definition. Next, we have the mass properties, mass balance. So that's your center of gravity, your moments of inertia, your ground reactions, including spring coefficients, etc. Then we have a flight control section. So basically, you need to do a flight control mapping from PX4 to JSBSim internally. That can be one-to-one, kind of depends on how you did your aerodynamic analysis. In our case, wanted to be able to sum trims, also how you treat the A-tail, whether you break that out into a rudder and elevator or if you have that directly modeled. Speaking of the aerodynamic model, we then have the aerodynamic section, which is kind of the bulk of where the OpenVSP work was affected. So we used a coefficient build-up method to model the aerodynamics. So that means we have coefficients relative to the contributing factors for lift, drag, pitch, roll, and yaw. And then the kind of final section that will lead us into our key JSBSim insight was the propeller and torque modeling. So this was a major finding for us, that one of the core assumptions in the thrust and torque generator in JSBSim, there's some assumptions built towards larger vehicles, so larger in size and weight than the UAS that we were trying to model. And so using the built-in thrust and torque generator, could lead to some instability issues, specifically when simulating vertical flight. So what we did is, because JSBSim is very extensible, the XML definitions support calculating and applying forces directly. So we were able to model the thrust and torques directly as forces in JSBSim. So that was able to circumnavigate that torque generator assumption internal to JSBSim without modifying JSBSim directly. So we found that to be sufficient and a very helpful thing for us. So now into the what. So the applications going forward. We kind of see two big takeaways from this work thus far. The first is that we were able to implement this solution in a very low power processing environment. So the whole JSBSim to PX4 interface, additional sensor simulations, all in hardware that's kind of roughly equivalent from a processing perspective to a Raspberry Pi. So we found that to be very powerful for not a lot of required power. The other takeaway here is the ability to create an airframe digital twin. It's extremely powerful. So to have an actual digital twin of the UAS, given a relatively short turnaround time to conduct rare, normal, and non-normal testing. So specifically things like locking up control surfaces, sensor variants, motor failure, weather conditions, all of that testing on a digital twin of the vehicle, we believe will lead to a path for software regulatory compliance for this enhanced level of software testing. So we think that's a really powerful concept. And I've got a demo here to just kind of show this in action. It's a very simple demo. We have Q ground control on the right there. Just a simple VTOL flight plan. On the left, we have the FlightGear visual model. So you see the visualization there. That FlightGear is running at 30 hertz, but the JSBSim on the back end, it's actually simulating the dynamics, is up at 250 hertz. So one of the things that we found really powerful about this is the ability to interact with the vehicle just like you would as an operator in the field. So from both a training perspective, but also from a tuning and flight planning perspective, since the dynamics of this vehicle are simulated sufficiently close to the real vehicle, you can use this for tuning. So as you see here, going to the tuning tab on Q ground control, tuning in the same way that you would tune the vehicle out in the field. And this is directly applicable and transferable to the vehicle. So we can tune it in the simulator, we can adjust our flight plans accordingly, we can fly everything in the simulator, take those parameters, load it on the real vehicle, and go. And so we found that to be very helpful, especially with the large vehicle class that we have flying here. So kind of talk through most of the flight, but as you can see, we're going to loiter around this waypoint to line us up for approach as I change the perspective. And here we are doing a back transition. It's also helpful to understand in the simulator how long, from a distance perspective, the back transition would take, as the particular vehicle we modeled likes to fly, and so we wanted to have a good understanding of where that back transition would finish. So there, we just completed it. We're over our land waypoint, and we're descending. So again, just a quick demo of that running live. Still going to land here, but we'll go on to the next slide. So kind of all the data that is available in PX4 is extreme. We all are aware of that. There's a ton of data that's available. But now with this solution, there's also the JSBSim data that is accessible. So in this slide, we have just a sampling of some of the representative JSBSim data that's available. So we were talking earlier about static margin analysis. This data is extremely powerful in helping us understand what was going on. So we see in the top graph here on the left, that red line is the start back transition. The top graph is the moments that are calculated from JSBSim. The graph in the middle is JSBSim's internal representation of the actuator outputs. And the graph in the bottom are just 3 of the forces that JSBSim resolved. So drag, lift, and weight. So again, in addition to the PX4 data, we found the JSBSim data to be extremely helpful. And then, as we said before, this is a very high-level presentation. OpenVSP has a whole workshop. We actually have the overview linked in this slide. I encourage you to check out some of these resources. These are a lot of the resources that we used to go and develop this solution and implement it. So could be something really helpful going forward to consider. So at this time, we can move to the Q&A session. And thank you for listening.
All right. So Jesse.
Yes.
Are you, I think you're live there. Yep, you're good.
I'm just gonna turn off my screen.
Go. All right, so we got a couple questions here. First question, can you say more about how to think about using this data for regulatory compliance, especially FAA type certification?
So I think one of the powerful things is with JSBSim, there's scripting capability. So you can run not just one flight that's very manual and intensive, but large batches of these flights, different flights, different flight conditions to demonstrate time on the software version or time on the hardware version or both. So I think that's just one of many paths that would be helpful for regulatory compliance.
Next question, did we evaluate AirSim?
So yeah, we had taken a look at AirSim. At the time, the openness and extensibility of JSBSim was kind of what drew us that way. And that there had been some work in that area that we had found. There's absolutely nothing precluding AirSim from being plugged in either instead of JSBSim or alongside. And that would be something we'd welcome going forward in the future.
Next question is, are there any plans to contribute upstream of the JSBSim integrations to PX4?
Yeah, so I believe we're working right now with Auterion on getting that code, the JSBSim to PX4 code released. I think a lot of these resources will help kind of point in that direction. So even without the direct source code, as we work through that timing process, I think that bridge is relatively accessible, even from the content we've provided here.
Next, and we'll use this as the last question. What's the advantage of using JSBSim instead of Gazebo?
Yeah, so the 6 degree of freedom model, basically with JSBSim, we found to have some advantages over the way the physics are implemented in Gazebo. So nothing precluding adding those elements to Gazebo, but since JSBSim kind of already has that view of the world built in, specifically with fixed wing flight, not only with fixed wing flight, but if you look at what JSBSim's traditionally been used for, having a large VTOL and trying to tune fixed wing dynamics, JSBSim kind of lends itself to that. Gazebo could be dropped in. I know, especially with the integrations with Ross and just the community that's around Gazebo. That's why we mentioned it before. Would also be a good solution either alongside or potentially in place of. But we found JSBSim even more attractive for the digital twin component of what we were looking for. Great. So
I think we're up on time. We'll look to answer any of the other questions online as possible. Thanks, Ramon.
Thanks.
All right, can you guys hear me okay? These guys are the real deal, right? Matt, Jesse, thank you for your amazing presentation. I'll talk to you soon and I'll see you on Slack.